Staying in town?
Me and my best friend and her sister are basically had Thanksgiving together, and
Oh, cool.
I'm smoking a brisket for the first time, and I'm really excited.
First time, yeah? Good luck with that.
I got the wood chips and everything.
Good luck.
My family decided to start some shit the other day, so I picked up an extra shit.
Oh, you don't want to be home?
No, don't want to deal with my family.
I used to enjoy going home for Thanksgiving every single year, and I picked up a double and be like, sorry, can't come.
Yeah, at least I'm working Christmas, so.
For 8.6, I remember.
Started. You all ready? So I was told I need to do the video again, but last week I didn't even post it on YouTube. No one said anything. So I was like, I'll put it up. I'll put the video up. All right. We are doing vectors today. So we're switching gears, and the notes that I have for this that I'm going to put on that TV screen, these are actually the notes directly out of my Cal 3 class. All right. So not to scare you, I'm just saying, like, vectors are vectors. It doesn't matter what class you're in. And in Cal 3, we do a quick review, kind of introduction review of vectors. So I'm going to follow these notes and do some examples from here. And I just want you to keep in mind that in Cal 3, we work both in two-dimensional space and three-dimensional space. So my notes are going to have things for both two-dimensional and three-dimensional. We're going to completely ignore the three-dimensional, and we're only going to do two-dimensional stuff. All right? Ready? So we're switching. I mean, this is a pretty big switch of gears here to be talking about vectors now. So it's not that we're done with triangles. We're going to actually tie back into triangles when we get to the end of this. All right, so vectors. Okay, what are vectors? Vectors are objects with two main properties. Okay, so I'm going to put most of this on the board, but vectors, some of this stuff is animated, so it's better. sorry about that. I'm going to write most of it, but there are certain things you might need to see that I'll move things around, so you'll want to see the screen. So vectors, what are they? They're objects with two properties. The first property is what? It has a magnitude, a length, okay? They have a length. We call this the magnitude. And it's also called the norm. Okay, the norm, in other classes we call it the norm. The magnitude, norm, or length of a vector. And then the second thing is they have a direction. Which is the way it points, all right? That's it. That's what the definition of a vector is. It's something that has both a length and a direction, some way we can orient it. Now, the geometric concept of a vector I've put up here in two-dimensional space is this. Take a flat sheet of paper, and what we're going to draw on this flat sheet of paper is what we call a directed line segment. Okay, so we're going to start at some point. We're going to draw to another point. Now, normally, we would call that a line segment, right? It's not a full line. It doesn't go forever in each direction, right? It's a line segment. But what I'm going to do is I'm going to give this some sort of direction by saying that it we're pointing in this direction, okay? So it's like you're starting here, stopping here, instead of starting here and stopping there, right? This, do you agree that if you look at this, it would qualify having both of these properties? Do you agree that we could have a concept of a length to it, right? It has some sort of length, which would be this measurement here. Let me do it on the other side. So this geometric object that I just drew has a length and it has a direction, a way that it points. And to see the direction, imagine coming out this way with like an imaginary, almost like an x-axis. And do y'all see that you have an angle that it forms there? We call that theta, right? So that object that you see in front of you is a vector. All right? It has a length and it has a direction. Now when it comes to vectors, we like to label them, okay, call them something. We could call that vector whatever we want to call it. So we're going to call it V for vector. Does that make sense, right? Nothing fancy there. I want to call this thing V. Now, when we write the letter V, you know how in this class we've used all sorts of variables, x, y, right? Theta. Those are things that we usually have used to represent variables. Those have always been just numbers, haven't they? Like x equals, and usually it's a number. Theta is some sort of number, right? V is not a number, it's a vector. That's something different than a number. So what we do to let you know I'm talking about something that is a vector is I draw this on top of it. Okay, now what that is just imagine taking like an arrow like that and just cutting the bottom of it like that off. Okay, that's the symbol we put above the V to let you know I'm talking about a vector, as opposed to something like x, which would be a number. Understand the difference? In textbooks, they sometimes use this notation, and they sometimes just do a bold V. Now, when I'm writing on the board, it's hard for me to do bold, right? Like, how do I do bold up here? So it's easier for me to do this little half arrow above it, and that lets you know I'm talking about a vector V. Okay? Now look, on the screen there, I can change, I think, where is it? Here we go, I think. I can change the length of this vector, right? I can move this around, okay? I can move this around, and I get a different vector, right? If I change the length and change the direction, I have a different vector. The important thing to understand about this vector is that it is not, I'm going to say this in the next slide here. When you look at this vector, its position on the page does not matter. Okay, so if I take this, imagine I just take this, pick it up, move it over here, move it down here, and draw it like that. If it has the same length and it has the same direction, then that's the same vector. Where it lives on the sheet of paper is irrelevant. All right? That's what makes vectors important. I'll give you an example. If I take this chair, right, and I want to grab it and I want to pull it across the room, right? I pull this like this. I am applying a force at this angle, right? I'm applying a force to this chair. Now, as I apply this force, I'm moving, the chair's moving, everything's moving, right? But the force is staying the same the whole time. So we need a way in the real world to represent something that where you put it in the space doesn't change what it is. Okay, so it's like here's the chair. Okay, that's my chair. I'm pulling on it with the force, right? And as I move across the room, if I'm in a different position, that arrow's the same. Well, it's supposed to be the same, right? Same length, same direction. So that vector there is the same as that vector there. They're equivalent, all right? Some terminology. That's three-dimensional, we'll skip that. Some language. When you look at a vector, right, this is the notation for it, V. This is also known as, we call this also the displacement vector, right? Displacement vector. this point that we start at, okay? This is called the initial point. All right? Also referred to as the tail of the vector. The tail. And then the other point up here is called the terminal point. Also referred to as the tip. All right? So when you draw a vector, you go from the tail, draw out to the tip. That's the direction we're pointed in. Now just to make sure you are understanding this, if I were to take this, let's make a copy of it over here. That's V, okay? If I go the other way, I start here and I draw this way and do that, is that the same vector? No? Why not? Why is the black one not the same as the purple one? Tail and tip are different, right? So what's different? Do they have the same length? They have the same length, don't they? So what's different about them? The direction, right? If you think about the black vector here, right? Think about that black vector. If we come out to the side like this and think about the angle here, right? That's our angle theta. Notice that those are two different angles, right? So the purple and the black vectors are both vectors, but they're not equivalent vectors because they have different angles. Same length, different angles, right? Let me ask you another one. Let's take our first vector over there, V. Okay, let me tell you that's V. What if I take this vector? Start here, stop right there. Are these vectors the same? No? What's different about them? Their lengths. Now they both have the same direction, don't they? Their direction's the same, but the lengths are different, right? So in order for vectors to be equivalent, they have to have the same length in the same direction, and then they are the same vectors. Questions? There's nothing, I'm not trying to trick you here. If this seems straightforward, good, all right? We good so far? All right, we're moving on. Two vectors are said to be equivalent if they have the same magnitude and direction. Okay, so that's what I just said, right? As long as they have the same magnitude and direction, they're equivalent vectors. So I have an example here on the board for you. See that vector? Look at this vector. Right? Are those two vectors equivalent? Yes, they have the same length, same direction. If I move it up, doesn't change anything, right? Doesn't matter where I put this vector, as long as they point in the same direction and have the same angle, then they're equivalent, right? All right, now, how do we determine a vector if somebody gives us 2 points on the xy plane? So let's say you have a flat sheet of paper here. Let's say that this is your flat sheet of paper. There's the origin. Let's say that I want to create a vector, all right? And I'm going to start at a point which is going to be my tail. Okay, I'm just going to start here. Now that as a point, we would write the coordinates of that point, and I'm going to call this x1, y1, right? That's a point. Then I have a separate point, which I'll call over here x2, y2, right? Now, can I create a vector between those 2 points? Y'all see a vector I can create? How many vectors can I create between those 2 points? 2 of them, right? I could go from here to here, or I go from here to here, right? Right? There's 2 different ones. So let's do the one that goes from here to there. So I want to create this vector, goes from here to here, like that. And let's call that vector V, all right? Then we have some new notation, all right? Some new notation. The way we're going to write this vector, V, is as follows. We're going to write V equals, now we're going to use this thing called an angled bracket. Then what we'll do is we'll go x2 take away x1. All right, that's the difference in the x coordinates. And then y2 minus y1. Angle bracket. Now, you know what? I want to label something. Let's call this the point A and this the point B. This point here I start with. This point here is where I end. I'm going to go from here to here. This is new notation for us, right? If you've never seen vectors, then we've never used those angle brackets before, right? This is brand new for us. Anytime you use an angled bracket, what you're doing is you're letting me know that you're talking about a vector as opposed to a point. With points we use parentheses. With vectors we use angle brackets. So this right here, what this vector represents, this right here is the vector from the point A to the point B. And that's it. That's the definition of it. So one thing I'm going to point out to you on this formula, it's subtle, but it's critically important. Notice that if you were going from A to B, notice which points come first. You do the x2 here, y2, right? And you subtract the x1 and the y1. So it's like if I want to go from here to here and create the vector, I take that x-coordinate, subtract that x-coordinate. That's what goes in the first spot here. And then in the second spot, I do the y2 and subtract the y1. Got it? Now, what if I wanted you to look at this vector that started here and goes this way to here? Let's call that vector W. What do you think this would look like in here? What do you think? If I reverse the direction, if I start here and end here, then what do you think goes here? This will always be the x's and this will always be the y's. It's flipped, exactly. So you're going to go x1 take away x2, and then over here you'll do y1 take away y2. You'll see the difference between those two? You're flipping these. You're flipping them because you're going the other direction. You're going from here to here. We're going to do an example. I just want to get the formula up here first. So let's go and write, this is the vector from B to A. All right? So we reverse it. Let's do a specific example. So as a specific example, let me give you 2 points here. Let's go with the point, what if I tell you this is the point -3, -2, and then let's take this point over here to be the point 5, 3. And let's call this point right here A, and this point B. First thing I want us to find, because there's two different vectors I could create here, right? I can go from here to here, or I can go from here to here. Let's do the one from A to B first. So if we go the vector from A to B, that goes here, points to there. Let's call it V. V would be, okay. It's always going to be the difference of the x coordinates, difference of the y coordinates, but you have to get the order correct. So the way I think about it, I don't know, everyone's going to think about this a little different. If I'm going from here to here, I always start with that x coordinate and subtract this x coordinate. And then I do that y coordinate, subtract this y coordinate. So what should I write here for my first piece? What minus what? 5 minus negative 3, right? 5 minus negative 3. And then the other one will be 3, right, minus negative 2. And then that's just angle bracket 8, and then the other one is 5. That's the vector 8, 5. So what I'm trying to get you to see is that if someone gives you 2 points, how do you write the vector that connects this point to that point? How do you write that as a vector? That's how you write it. You write it angle bracket 8, comma 5, close angle bracket. No questions? How about the other way around? What if we go the other way? Let's go and do it from here down to here. Call that W. So W would be angle bracket, angle bracket. Let's see. This time I'm starting here and going to this, right? From here to here. So we're going to do this x-coordinate minus that x-coordinate first. So negative 3 take away 5. And then I do this y-coordinate, negative 2, take away 3. And you get negative 8, negative 5. Those are very similar, aren't they? The difference between those two vectors is a negative sign, right? It's like that 8 became negative 8, that 5 became negative 5. Questions? I give you 2 points, you can create a vector? Yes? Okay, let's move on. The zero vector. So the zero vector is a very special vector. It's the only vector that doesn't follow any of the rules of the other vectors. The zero vector is the vector, we write it like this, 0 with the vector symbol over it. This is not the number 0, okay? The number 0 is the number 0, the way you've always known the number 0, right? When you write 0 with a little vector symbol over it like that, what this is the vector 0, comma 0. See, it's this vector where the two pieces you have inside are both the number 0. What's unique about this vector is that it doesn't have a direction. Remember I said a vector has to have a length and a direction? Right? That's the way I defined a vector to start, isn't it? What do you think the length of that vector is?
It's a point.
It's a point, right? So how long is it?
0.
0, right? So the length of that vector would be 0. So it does have a length, right? 0. But what's the direction of it? Well, if it's a point, then there's no direction, right? So it's almost like undefined, or it points nowhere, or you could say points everywhere. This is the one special vector that doesn't play like the other vectors play, right? Every other vector I draw other than this is going to have some length and some direction. But it's an important vector because of where we're headed, all right? We have to define this before we can proceed, all right? All right, now some more language. All right, components of vectors. All right, so when I write a vector, like the vector v, I write it with an angle bracket, and then another angle bracket, and then I'm going to have some number here and some number here, right? I'm going to have 2 numbers here. In the previous examples, we had 8 and 5, and then the other one was negative 8, negative 5. Either way, these are just numbers. So I'm going to call this first number v1, v subscript 1, and this other one v sub 2. So I'll do an example next to this. As an example, when we had that vector just a second ago, it was 8, 5, right? The 8 was my V1, the 5 was my V2, right? V1 and V2. Just what are those numbers? When we write a vector this way, this piece right here, this first number, is called the x component. The x component of the vector. And then this V2 is called the y component. This is just language, okay? We just need to make sure we all understand the language in the notation that we use when we talk about vectors. The thing that students get confused on is if I write, let's just say I write this on the board. I write 4, -3 versus 4, -3. Look at those two things. This is a point. I could go to the right 4, 1, 2, 3, 4, go down 3, 1, 2, 3, put a point in here. That's what this is, okay? This is the point 4, -3, right? This is not a point. This is a vector. And what it has as its property is that, I'm going to try and do it this way, is that if I went out 4 and down 3, I would be at that same point, but it's actually the vector that goes from the origin to that point. It's that object right there. It's this right here is the vector, right? As opposed to that, which is a point. So when you look at a vector, this number here is called the x component of the vector. That's basically how long that direction is. This is the y component, which is how long that direction is. This is called the x coordinate of this point. This is called the y coordinate. So that's the difference. Coordinates of the point, components of the vector. Two different words there. All right, now we get to the first real big thing with vectors. The first big result. It's called the parallelogram law. And this has to do with what we refer to as vector addition. Okay, so vectors are these objects, right, that have a length and have some direction. And the first thing we're going to learn to do with them now is how do you add two vectors together, right? So what happens if you take a vector and add another vector? This is actually a bigger deal than you might think, because if let's say I gave you that point right there, okay, and then I gave you some other point. How about I gave you the point -3, 2? See those 2 points? I could plot them. Can you add 2 points together? Does it make any sense if I give you 2 points, say, hey, add them together? Does that make any sense to us? No, right? Right? If I just give you 2 points on a flat sheet of paper, say add them, what do you do, right? What do you do to add them? Well, with vectors, we can add them because they are objects that have some length and direction. So when we add them, what we can do is kind of paste them together. Remember, vectors can move around wherever, once I have a vector established, it can slide around up, down, left, right. As long as I don't change the direction or length, the vector stays the same. So let me give you just a generic picture. Let's say I give you, to make things easier, let's orient everything at the origin first. I'm going to give you a vector here. We call this vector that goes from here to here. I'm going to call that the vector v, all right? Then I'm going to give you another vector. And let's do this one. It's going to be a shorter vector. It's going to stop right there. I'm going to call that one W. Do you agree I've given you two vectors? They both have a length. They both have a direction, right? Two different vectors. I would like for us to find what V plus W is. Now, I haven't told you how to do this, right? I'm about to tell you what this vector addition means. So am I allowed to take this W? Can I take this W vector? Can I move it up and down? Will it stay the same if I move it up and down? Yes? Can I move it left and right? Yes? Doesn't change? I just can't stretch it out, right, and change the direction. Then it's not the vector anymore. Same with V. I could take V, I could move it up or down, right? I could move it left or right, and it's still the same vector. So to add these two vectors together, what I'm going to do is I'm going to leave one of them alone. Okay, I'm going to leave the red one here, in this case, alone. And I'm going to take this blue one. Okay, let's imagine I've got my blue one here. What I'm going to do is I'm going to slide it over, and I'm going to move it up like this. Okay? And what I'm going to get is I'm going to attach, let me move it up there. I have to try my best to make this look right. Y'all tell me whether or not this looks to you to be parallel in the same length. Does that look parallel and about the same length? The blue one? These two, close enough? Close enough? Okay, so there's W there, right? That's the same vector, I've just moved it. But I have taken the, how would we say this? I've taken the tail of W and attached it to the tip of V, right? Tail of W to the tip of V, tail to tip. And then, does that make sense to you that this would be what it means to add the two vectors together? Okay, so what's the answer? Our answer should be a new vector. And do y'all see the new vector? It's what would happen if you started at this point, moved up through the red, and then through the blue. You would finish here, right? Which is equivalent to going straight across to there. That right there. This vector right here is V plus W. So if you have two vectors and you want to add them, you take the tail of one and attach it to the tip of the other. And then you draw a vector starting from where they both started, right here, and you go to where they ended. And that right there is your new vector. Now, I just did this and I attached the tail of W to the tip of V, didn't I? Tail of W to tip of V. Could I have done it the other way around? Could I have done the tail of V to the tip of W? Well, what would we have gotten? Let's leave the W alone. Let's take the red one and move it so that the tail of the red one touches the tip of this one. And do y'all see what we get if we do that? Where do we end up? Same place, don't we? We end up at the same place, right? This is V, and so we wind up at the same exact place. Here we did V and we added W. Here if we do W and add V, we all wind up at the same place, and therefore the answer is the same. You'll see it? Do y'all see why they call this the parallelogram law? Do y'all see the parallelogram? The red vectors and the blue vectors of this parallelogram. And so anytime you take two vectors and add them, you can look at it as a parallelogram, and your answer is the line connecting the two points across the edge, like the two opposite points. With me? Okay, let's do another one.